Okay, so when we move the ball, it's just a solid ball. The air adjusts, but for the calculations of the ball itself, its motion, whether it's unstable or wave solution, we didn't have to worry about how the air moves. Whereas if you do it in a fluid, you're going to move a parcel of fluid within the fluid, so the other part of the fluid is going to adjust, right? That's going to be critical. So when we talk about convection in the ocean or in the atmosphere, stability concepts are the same as we saw at the ball at the top of the hill and the bottom of the hill and so on. But the thing you have to remember is that when we move one parcel of fluid, there is continuity and the other part of the fluid adjusts. So we'll create concepts of a parcel that's moving within an environment. So we will worry about pressure, temperature of the environment versus pressure and temperature of the fluid that's moving within the environment. So we need the concept of buoyancy for that, because unlike the ball rolling on the solid surface, here we have relative density difference of a parcel of fluid. If it gets lighter with respect to the environment, or if it gets heavier with respect to the environment, it's going to have a buoyancy that's different from the environment, right? So the motion is going to depend on the relative density, so buoyancy. Okay, so here is where hydrostatic begins to be more and more important, because we are assuming that the atmosphere is firmly set in hydrostatic balance. So at any point, if you move a parcel, the pressure is going to adjust to the mass above it. Remember that the hydrostatic pressure says the pressure at any point is equal to the mass of the air above the parcel's position, right? That's what the dp dz equals minus rho g ends up being, and you integrate from that position to the top of the atmosphere. Very good. So let's look at two positions in a water column here. You have A1, A, and A2, and B1, B, and B2. Somehow we have created a buoyant parcel at B. So pressures at A, A1, and A2 are the same. Okay? Whereas at the bottom we have created a lesser pressure at B, which means the flow is going to be from higher pressure at B1 and B2 into the lower pressure at B, which is going to push up this buoyant fluid, which is going to move up to A. But at A, its pressure has to adjust to this to be the same as A1 and A2. So you can already see that the pressure gradient is pushing the fluid up, because you have created a buoyancy there relative to the fluid around. The same thing can happen if you create a heavier fluid here. Flow is going to go away, and then water has to come up. So we will look at those two situations on how you can create convection either by warming from below or by cooling from the top. Okay, so the main concept we need to define here is that the density difference is going to matter. Okay, relative density is going to matter. So the gravitational pull here is going to be delta rho over rho p, where p is the density of the parcel that's moving within this environment with a density of rho e. Rho e is density of the fluid around. Parcel is something that's moving within. Why do we call it a parcel? Essentially, we'll introduce the concept of adiabatic movement, which means the parcel is moving so fast relative to the environment that no diffusion of heat can happen. Diffusion is a slow process, so if you move fast enough, only way it can happen is by mixing or expanding and cooling. Okay, so if it is an incompressible fluid like water, here we are talking about water. So water is basically incompressible. pressure effects are very small. So if it moves from one pressure to another, it's not going to expand or contract. So it's not going to do any work on the environment. Whereas in the air, when we see later on, as soon as it moves and pressure changes, it's going to expand or compress based on whether the pressure increased or decreased, because air is highly compressible. Okay, so it is this concept of the difference of the density of the parcel and the density of the environment, delta rho, and the ratio of that with respect to its own density. That's the buoyancy. Okay, buoyancy B is going to be minus G, because if rho P is greater than rho E, it's going to be negative, which means it's opposite direction of gravity, so it's going to go up because it's buoyant. Whereas if rho P is less than rho E, that's going to become negative, and this is going to become positive. I said it the other way. If rho P is less than rho E, then the buoyancy force is positive, so it's going to go up. If rho P is heavier than the environment, obviously gravity is going to pull it down. This is going to be a negative. Okay, good. So this is called reduced gravity. Why? Because you're in a fluid that has density, and your buoyancy is going to depend on the relative density with respect to the environment. The gravitational pull is going to depend on that relative density. Hence, it's a reduced gravity. Gravity effect is reduced by having density of the environment being different than your density. Okay, so buoyancy is minus G times density of the parcel minus density of the environment divided by rho P. So if rho P is less than rho E, then the parcel is positively buoyant and rises. If rho P is heavier than the environment, then it's negatively buoyant and it sinks. And if it's equal, obviously it's neutrally buoyant. So we defined a basic concept of buoyancy and reduced gravity. This becomes very important in the atmosphere and the ocean, because you're moving fluid within a fluid. You're moving a parcel within a fluid, and because of this motion up or down, or sometimes horizontally, the density and pressure and temperature are going to change, and they are all related to each other. But we are going to keep insisting that the system is in hydrostatic pressure, because typically, despite a lot of the motions happening, the system is almost always in hydrostatic pressure. So the adjustment processes must be such that hydrostatic pressure holds.